Hi everybody, my name is Dr. Christopher Collison, and today I'm going to talk to you about some of the background behind the work that's being done in my research lab, and the title of the presentation is Mechanisms, Photophysics and Materials Design for Optimized Organic Photovoltaics. And what you'll see here in the animation is something that we'll explore as we go through the presentation. As these two Squaraine molecules start to come closer and closer together, what we can observe is a change in their absorbance properties. And we'll explore this as we move forward. So here's the outline of the talk. I'll give you a summary of the story in a few seconds. I'll talk about organic photovoltaics in general, why we would care about them, the importance of efficiency and photophysics, as that influences the mechanism and the efficiency of the devices. We'll talk about how they work. If we know how something works, then we can actually think about improving the device. I'll provide a few snippets of device data. I'll then talk about something called exciton diffusion and how it relates to the spectroscopy that we can measure in the lab. And we'll also talk about these aggregates, and an aggregate is what you get when these Squaraine molecules that we're interested in, when they start to pack closely together, sort of in a stacked form, like I'm showing here. So, and then I'll conclude. So the story in a nutshell, this is really the why I'm looking at what I'm looking at. And what we can recognize is that there's a problem. We have a major problem in climate change for our planet. 2019 was the second warmest year on record. This is behind 2016, which was the warmest. But what we're going to find is that the last 6 years, actually that should be 6 in here, rank as the 6 warmest years on record. So let's actually take a look at the data. You can find all this data at this website in here. Let's take a look. Here are the rankings, and what we can see here is if we go all the way back to 2014, all of those last 6 years are the hottest years on record since 1880. So climate change is a reality. The anomalies here in degrees Celsius, or of course in degrees Fahrenheit, this is how much hotter than the average our planet has become over the last 6 years. What else can we look at? Again, we can find more of this information on the NCDC, on the NOAA website, but basically this is showing how much there's been a change in the global temperatures over the last 6 years. So actually these dates give the top 10, or these images give the top 10 years, and what we'll see down here is actually here's our baseline, right? So here's our baseline, this is 0, and this is the anomaly. So this is how much higher those temperatures are than our average baseline. In case we didn't have enough gloom and doom that hopefully would shake us out of our comfort zone to try to do something about it. This is actually 40 years of history in the US for $1 billion climate disasters, and this is a frequency. So this is the number of events here on the y-axis, and what we can see already, this is the year 2020. We can already see that there are a large number of $1 billion costing disaster events that are occurring, and we'll see that in the last few years. So we've got 2018 in here, says 2018, 2019's in here, 2016 is there, and then 2011 up here, and 2017 in here, and then last but not least, we're already making a big impact in 2020. That the time that I'm talking to you at the moment is September, but this is the data that we have on hand at this time. So these statistics are valid as of July 8th, 2020. So again, the real impact, let's look at some photos. We know that the polar ice cap in the Arctic is decreasing in size, and we can see that there's about a 10% drop in Arctic polar ice cap coverage per decade, and this is continuing over the last 4 decades. And so again, we can also get information from the National Climatic Data Center in here, and this again just shows how humidity starts to go up as we have warmer air. That warmer air can actually hold more water, and of course we also know this as when there's more water held in the air, we get more catastrophic rainfall, which starts to do damage, and this is where all our dollars are spent in repairing these things. We'll see more of that as we go forward over the next few years, I'm sure. So, where does this carbon dioxide, that's really the root cause of all of our problems, where does that come from? It comes from largely the burning of fossil fuels, and we've been relying on this for energy for a long time. Of course, it also comes with climate gases or greenhouse gases, things like methane as well, which come from over farming and meat agriculture in particular. But we'll talk about renewable energy in this presentation today. And renewable energy should be the answer for us. So let's have a look at one particular range of renewable energy solutions, and these would be solar cells. And the solar cells shown in this graph in here, what we have on the x-axis is time, and what we have on the y-axis is the world record solar cell efficiency. So we'll find that a lot of the solar cells up here in the top right hand corner are very expensive sort of multi-junction cells that have very niche applications, satellites in space, where the expense of these things is nothing compared to the expense of sending a rocket into the sky. But what I'll be talking about predominantly will be down in this region, and what we see is for organic solar cells, we see this sort of increase in efficiency over the last 20 years that starts to rival the sort of efficiency here of silicon solar cells. Of course, silicon solar cells are becoming very inexpensive because of the economies of scale of mass production of these things. But there's also we like to think of there being a portfolio of different solutions for solar cells, and so the remaining parts of the talk will be on this area here, and of course, if we really want to understand how progress can be made in solar cells, well, let's understand these materials down here, since that's now the focus of the rest of the presentation. So what we do in my lab, I actually work with Dr. Cody in the School of Chemistry and Materials Science, and he makes materials for me. And in my group we do a bunch of characterization and device testing. And then I work with Dr. Frank Spano over at Temple University. So he works with me to do a lot of our theoretical investigation as to why these devices might work based on the materials properties. And what we pull out of those theoretical investigations, we correlate that with the efficiency of the devices. And so once we understand how we can change the materials, how that influences the properties, we can validate the theory. We look to improve the efficiency. All this helps us to do what we call rational design. It provides us with design principles that allow us to kind of go back on this circle, back on the loop, and then we come up with more molecules to synthesize, and onwards around the circle we go. So We work with Squaraines. I mentioned that in the first few slides, and Squaraines kind of look a little like this, sort of a green powder. They have a very broad absorbance in the film, in the solid state. So you're going to see, we have some very broad absorbance spectra in here. So absorbance is in the y-axis and the wavelength is on the x-axis. The black curves that you see in here, this is the absorbance of Squaraines in solution. So it's very important to be able to absorb over a wide range of sunlight, of colors in the solar spectrum, and so that's why these Squaraines end up being good for us. They're pretty stable in air. Another key point here is they have very, very low synthetic complexity. So they can be synthesized in as few as 3 steps. And that's very, very typical for these materials, as described in a report by Poe and Roncalli from 2016. So these side groups determine the packing. So on these Squaraines, here's a Squaraine molecule in here. And then we can add these side groups, these R groups that we put on the side here. And these R groups basically represent different chain lengths in here. So we can have some alkyl chain lengths. And what that allows us to do is to keep these central Squaraine sort of moieties in here. Those are kept at bay or at some distance or in a certain stacking geometry. So we might have something called a slip stack geometry, and that's all governed by these side chains which we can control. So let's have a look at these side chains that we've made, Dr. Cody's made in a library of materials that we have on hand. So it's these side groups that determine the packing, but not the electronic properties of the material in solution. So if you can look at all of these graphs, what we find is that the black curve in here always stays the same, independent of what the Squaraine is. But when we change the side chain, we actually end up getting very different. The red curves in here are very different, and that tells us that those side chains and the packing are particularly important for their use in organic photovoltaics. We'll go on to look at why, but I'll give you a sort of punchline here ahead of time. We care about something called exciton diffusion, so we're going to remember this name, exciton, and they also affect the charge carrier mobility. So carriers here we're going to talk about as electrons and holes. So let's look a little bit more at how photovoltaics are made and maybe the commercial benefit of working with these organic photovoltaics. So why would we care about them? So why commercialize them? And what I'm showing from some of these images are a bunch of commercially available solar cells, in this case by Armor, by a company called ASCA. We also have materials shown in here from a company in Germany. Heliotech make materials like this. Merck make those materials. And these are, of course, some devices from my labs. You can see all the different colors that are available from a range of different materials that we work with. So benefits, environmental advantages, there's no lead or cadmium in these materials. Fairly short energy payback time. So in 6 months, we can recoup the cost of the environment actually of making these devices. In principle, we can do some low cost printing on flexible substrates. So we can also get, as I mentioned, different colors. Here are the different colors up here. Semi-transparent or transparent. We can put those into different glasses, and we can actually control the color of the glass in buildings, for example. All beautiful. However, these things ultimately do have to be efficient. Heliotech is a company that makes solar cells, and they use a roll-to-roll printing approach, as you can kind of see in this factory photo. And in principle, you can cover, if these things are so inexpensive to make, so you can cover up concrete, you can cover up building facades. So this is where we talk about this aesthetic integration. If we want to move from prototype to full-scale manufacture, well, there are some challenges. Most of the time in my lab, for example, we work with something called spin coating. So we drop some solution onto a spinning chuck where there's some a glass substrate perhaps that sits on the top, and as the chuck is spinning, what happens is the liquid starts to get thrown off the side, the solvent evaporates, and we're left with a very uniform thin film. It's very useful for making one particular substrate, one particular film, but it doesn't translate well into what we would call roll-to-roll printing, where effectively we're trying to coat a whole large film that moves backwards and forwards across these rollers. We can do this in a discrete way, where we put down different layers of materials, and in a way very similar to the way that Kodak used to make film for cameras some time ago. Same principles. They could do that incredibly cheaply, at low cost, and that was a very profitable business for them. Of course, we can also do a sort of integrated approach where one particular solution is deposited, one particular film is deposited one at a time here, and here, as the film moves from from the substrate to the final product over on the right hand side. So this is the roll-to-roll printing, and in my lab, we're also working on ways to actually scale this up, to actually move from something from spin coating into something called doctor blading, and that doctor blading is a precursor to how we might use roll-to-roll printing in the future. And being in Rochester, New York, there are also some large pilot roll-to-roll printing systems available in town, and so Rochester has a lot to offer for the photovoltaics industry. So I've mentioned to you Squaraines. There are other inks. This is a material that's been used for decades now, poly-3-hexylthiophene. We also work a lot with C60 Buckminster fullerene in here, and a certain soluble derivative of C60, which would be called PCBM. The PCBM comes from this side group in here that enables the solubility for that material, and we've seen already the picture of the Squaraine in here. And again, I'll just state this again because it's particularly valuable that this Squaraine can be made in really a very cheap one-pot synthesis, very scale-up friendly. And from this report from Poe and Roncalli, these Squaraines have the lowest synthetic complexity of all OPV materials that were included in their 2016 study. So low cost, excellent. However, again, we have to think about how we improve the efficiency. So how do we do that? Well, we have to think about this mechanism of operation. So really, it's how do these devices work? Let's take a look. Here's a very simple cartoon. In this way, this is a kind of a zoom in here on the right hand side of this little portion in the middle of the active layer of the device, and what we've got going on here is electrons flowing around an external circuit. Okay, so we might think of electrons going anti-clockwise here. Electrons going anti-clockwise. Okay, and holes are going in here. Holes are going clockwise. So that's what we think is going on. Let me zoom in a little bit more, and I'll tell you about the 4 steps, these operating principles for these devices. So first of all, we need to have a transparent substrate, and this is our transparent substrate in here. It's coated with what has to be a transparent conductor, and this is typically indium tin oxide. The problem with this is indium is going to run out eventually, so that's important to find a replacement in the long term. We use molybdenum trioxide very often in industrial manufacture. We use something called PEDOT-PSS. It's essentially a buffer layer, and it allows holes to move through in one direction, prevents electrons to move in that direction, and so that means that the electrons end up having to go towards the top, towards the aluminum. Getting ahead of myself, so the idea here is we have light comes in through the bottom, and we have the dyes that are in this active layer. Here's our active layer, and here those materials in that active layer end up absorbing that light. Let's have a look at what happens when light is absorbed. We create this exciton. An exciton is a neutral excited state, and that exciton can migrate to a heterojunction interface. An interface, in fact, between these two materials. That's the red line in here. So that excited state must migrate to an interface. Why is that so important? The magic happens at that interface, and it turns out that at that point the electron and hole that are combined together in the exciton actually now dissociate into free charges, and that's important for generating electricity. How does that happen? And again, we're talking about materials here that are organic materials, and they typically have a very low dielectric constant, and so we tend not to consider that any one molecule significantly interacts with neighboring molecules. So we can't use band theory ideas. We do talk about the highest occupied molecular orbital in here, or the lowest unoccupied molecular orbital. Here is a molecular orbital where there are 2 electrons. So it's the highest occupied. That orbital is occupied. What happens is when we shine light on that system, we take one of those electrons, and now it jumps into what was previously unoccupied. It was previously the lowest unoccupied molecular orbital. And at that interface between these two materials, what happens is that electron will hop from one material over to the other. Why? Because the LUMO, in this particular case, the LUMO of the PCBM, these fullerenes, they love electrons. They have very low-lying LUMOs and HOMOs. So these LUMOs end up being a long way down, very low. And what happens is that electron sort of hops over here and stays in the LUMO of the fullerene. And this means that this fullerene now has an extra electron. So it would have a negative charge, and we're left with the hole, which is the absence of the electron on the left-hand side. So that's the importance of that interface. So now we have a little electron and a hole in here. Okay, they're actually black in the very small in the image that you're seeing, and what happens now is the electron will diffuse towards the aluminum, and the hole will diffuse towards the PEDOT-PSS, or the molybdenum trioxide buffer layer, because that hole, of course, can move through this material. And that's how the devices are proposed to work. So with each of these 4 steps, there are problems, there are efficiencies for each of these steps: the absorbance, the exciton diffusion, the charge transfer, and the charge collection. So if each one of these has a particular efficiency, you multiply them together, you get the total efficiency of the device. So there are 4 limits to efficiency and 4 things that we can tackle in here. So absorbance, exciton diffusion, charge transfer, and charge collection. Today's focus, we're going to focus on a few of these. Let's first talk about the extinction coefficient, the ability of a particular material to absorb light. And that's an intrinsic property of a particular material, and it's described by something, as I say, called the extinction coefficient. Let's look at some examples. Okay, so what I'm showing you here in this dotted line over the top here, you can see the dotted line continue. This is the solar spectrum in here. This is the number of photons per meter squared per second per nanometer. So that's what's on the y-axis. That's how many photons, how much light the sun is putting out. So we see a lot of photons out here in this near infrared region. Back in the time of this paper from which I took the figure by Gunes et al. In 2007, most of the materials started to absorb or absorbing in this kind of blue-green region in here, right? So they're not absorbing as many photons as we might like. We probably want to start absorbing a little bit more in this region because this is where most of the photons are. And they recognize this, and this can be quantified. And the idea here is that if we have a small band gap, okay, 1.1 electron volts, the statistics, the calculations would say that we should be able to absorb about 77% of the solar radiation. However, if we had a much higher band gap, 621 nanometers, that's in the sort of yellow region, yellow to orange region, then we'd only be able to absorb and keep about 30% of the solar radiation. So a lot of effort was put into making these lower band gap materials, and sort of a little figure to show you again what I've just described. So if we have a very large optical band gap in here, very large band gap, so this gap is large, we can only really absorb the very few photons. It turns out we can absorb maybe these photons in here. This is energy on the x-axis now, so there's the energy that we start to, the photons that we can absorb in here might just be high enough, so might just be high enough to be above this red line. So high energy means high voltage, but low numbers of photons absorbed and low number of electrons, and therefore low current. So the idea here really is that we need to be able to have a lower band gap in here. So here's our lower band gap, right, compared to this high band gap in here, and that means we can actually collect more of the electrons. We can actually probably collect a whole bunch of these electrons, including the UV ones. And what I'm showing in this image here is that even if we excite to a much higher energy level, we will lose some energy in terms of kinetic energy, but we still collect those photons, and we can still turn them into electrons that allow our device to be successful. So that's the idea that's shown in this particular image. So how can we actually work with a tandem device? In this particular case, a tandem device represents something where we start to absorb in the near infrared, and we add another absorber in here. This is poly-3-hexylthiophene that absorbs in the blue-green, and in principle we can start to absorb over the whole solar spectrum, and that's been a winning strategy for a lot of people in recent years. I can illustrate that in this figure. So here would be, for example, our Squaraine in here. That's the black curve on the right hand side. The blue curve is the solar spectrum, a little bit more resolution, and this red curve now that you see up here is the blue-green absorbing poly-3-hexylthiophene, and there's the image of poly-3-hexylthiophene there. And so when you look at this spectrum, this is the fullerene over here in the UV, but when you look at this whole spectrum in here, what you can imagine is now we start to absorb over this whole range of wavelengths, maybe from 300 nanometers all the way up to 775 nanometers, and that means the more photons we can absorb, the better the device. So I mentioned today's focus in part was associated with this absorbance, but we can also think about charge collection and charge mobility. Again, I'm saying each bullet here represents an opportunity. It turns out that if we can pack molecules tightly together, what happens is that the mobility increases, the orbital overlap increases, and it turns out that holes can move quickly through the material when that material is crystalline. So we'll come back to this. What else are we going to talk about today? We're going to talk about exciton diffusion. So what is exciton diffusion? It's a form of energy transfer. And the key here is, if these are blobs, if these are features, if these are domains inside our device, this is one of the Squaraines that we've been working with, and if these domains are about, I don't know, 75 nanometers in diameter, but let's suppose that the energy can only transfer 10 nanometers, well, we've got a problem, because supposing we excite an exciton in here, the problem is that exciton has to energy transfer. It has to energy transfer to the interface between the two materials. And that can be a problem. We need, of course, to get this electron to hop over into the other material. And what this means is perhaps we've created an excited state over here on the left-hand side, and this is now some description of distance. We've got to get this excited state all the way over to this interface between the two materials. So how does that happen? This is something called energy transfer. We can think about this. There's two forms: Forster energy transfer and Dexter energy transfer, and they have something in common, which I'll talk about in a second. We'll talk about Forster energy transfer. What happens is, as the electron, the idea is there's a dipole interaction. As this electron thinks about dropping back down to the ground state, at the same time, an electron in a neighboring molecule thinks about jumping back up. The energy is conserved, and what happens is that excited state will move from one material to the next. And so we see the same idea. The fluorescence in one molecule here, the fluorescence here will lead to an absorbance in the neighboring molecule. So how does that look? That excited state jumps across, so on and so forth, as that excited state gradually makes its way to the interface, and the electron can transfer from one material into the next. This rate of energy transfer is actually proportional to the overlap between the fluorescence, so here's the fluorescence of the energy donor, and the absorbance of the energy acceptor. So what we need, in fact, is, this is a crude diagram, but what happens is, here's our absorbance. We're going to see some absorbance. We go from a ground state to an excited state. We shine light, and each of these black arrows in here represents a photon of a particular energy. And what happens is we get some fluorescence, and if that fluorescence is allowed, so like a check mark here, yes, it's allowed, what happens is that energy, as we think about the excited state coming back down to the ground state, we can imagine a ground state in a neighboring molecule jumping up to the excited state. We need overlap between the fluorescence and the absorbance in order for this to happen. So this is spectroscopy. The spectral overlap here required is shown in this blue region in here, and this overlap in here, and that's sort of a summary of what's we hope is going on in our materials. However, what frequently happens, and certainly this happens with the Squaraines, is and maybe this is again revealing the punchline too quickly, but when we get aggregates, when these molecules pack tightly together, it turns out that actually this fluorescence is greatly quenched. Okay, it's greatly quenched, and so now we've lost all the overlap. We've lost that overlap integral, and it turns out that we think the energy transfer it seems to be, we would think, would be reduced, greatly reduced. So before we started all this, we also thought about we don't want a large domain size. Okay, because if we have a large domain size, we can't get our excited state to reach the interface, and so this would be bad for us. We don't always want a small domain size. If we have a small domain size, then if we have all these very small features in our material, it's very difficult to get the electrons out. It's a very tortuous pathway for those electrons to get out from the device. So it actually slows down the device and reduces the efficiency. So we don't want a small domain size either. We kind of want high crystallinity. If we have high crystallinity, that means we're going to have high intrinsic mobility. But it turns out that when we at least we think, when we're putting these molecules side by side, it influences the energy transfer rate. So that's not so good either. So we kind of want high intrinsic mobility. We want these super highways, so we might want some larger domain size, but it can't be too high because we can't get the energy to the interface. So we're looking for some kind of sweet spot, and that sweet spot we thought would be around here. We thought we'd want more crystalline. Made a lot of sense to us to have more crystalline materials, and we thought we could control that crystallinity by heating our samples up above the melting point and gradually cooling them down so that they formed crystals. That made a lot of sense to us. Here's some more images. Again, another way of looking at that same squared table in the previous slide. And what we were kind of looking for is this kind of sweet spot where we have just enough crystallinity in this sweet spot, so the molecules are tightly packed enough to get high mobility, but not too tightly packed that we would lose fluorescence and therefore lose energy transfer. So it's just another sort of way of looking at things. We can come back to this later, of course. So a summary of the key themes so far in the first part of this presentation. So yes, we work with these Squaraines. It turns out that phase separation, which we can control by heating up these materials, it creates these domains. We don't want the domains to be too large in size. We think that crystal packing is important for mobility, for charges, the ability of charges to move. That's conductivity, right? The mobility of charges through the devices. We also think that fluorescence in the solid state may be important for energy transfer. So that's a summary of the key themes so far. So now we're going to move to the second half of the presentation. So I'll throw in a small amount of device data. We'll talk about how we can quantify these aggregates and monomers, actually individual monomers, through using spectroscopy. We'll think about exciton diffusion, how we can measure that in the lab, and we'll think about whether that exciton diffusion is a problem for the aggregates, and then I'll conclude. So let's think again. Squaraines, push-pull systems. What does that mean? It's a type of family of material common in the organic photovoltaic world. These materials, I'm not going to go into that today, but these materials absorb in the near infrared. And the push-pull approach is to have a sort of donor-acceptor moieties, different donor-acceptor molecules that are connected together inside a single molecule, and this allows for so-called band gap engineering. So we end up getting lower energy band gaps, and we start to see absorbance more out towards the near infrared. So Squaraines are these very small molecules that are these representative push-pull systems. And we're also saying that they are panchromatic. Panchromatic means they've got a very large full width half maximum here. So they absorb over sort of 500 nanometers all the way out to 800 nanometers. The side group, as I've mentioned before, when we change the side groups in here, it affects the crystal packing, it affects the aggregation, and it also affects the compatibility and how well these materials mix with these fullerenes. And these squareines are particularly useful for testing theoretical models. So theoretical models are going to work on very simple systems. You don't want too many atoms in the molecule if you're working with quantum physics or quantum chemistry calculations. So because these molecules are actually relatively small compared to all the other OPV, organic photovoltaic materials, this is good for theoretical collaboration. So, as I said, it's time for a little bit of sprinkling of data just to kind of set the scene for the rest of the talk. There's some very early device data in here from maybe about 7 years ago, 6 or 7 years ago. So the efficiencies are really modest in here. So we've got about 1.09 efficiency, not a lot. And this is these dibutyl squaraine materials in here, unannealed, and we thought, okay, what's going to happen? We're going to anneal these samples. When we anneal these samples, what we find is we get this broadening of the spectrum, and what we've typically found is that as we anneal the spectrum, the efficiency decreases. Very preliminary data. We've done a lot of work since, but let's basically follow on with the presentation and say, well, really, why is annealing bad? And if it is this aggregation that's that we're getting in here, why is this aggregation causing us problems? So what we're going to look at here is actually what happens during this annealing process. So the annealing causes increased crystallinity and phase separation, in particular with this material, DHSQOH2. That's a hexyl side group. This hexyl side group, squaraine, does not mix well with PCBM. So if we have a 50-50 mixture in here, what we can see with these transmission electron microscope data is that there's already a significant amount of phase separation even in unannealed samples, and this is 25 degrees Celsius on the right hand side. What happens is as we increase the temperature, so as we anneal to 175 degrees Celsius, we get a very effectively these domains get larger and larger and larger, and at 75% PCBM, there's we tend to have a little bit of a better mixture, so we can change the in the unannealed samples, we can change the relative size of these domains. But again, here when we anneal for 3 minutes at 175 degrees Celsius, again we see this really significant phase separation, and we can see these very hard boundaries in here. So these materials are definitely purified. So the point here is that the blend ratios and the annealing conditions affect the domain size. So really what I'm saying in here, let's just come back to this image we've seen earlier. Annealing, what it does is it takes sort of amorphous, higgledy-piggledy oriented molecules and basically turns them into sort of more crystalline. But also we reach a point where we've actually phase separated. So we've separated here the fullerenes from the squaraines, and that's what annealing does for us in those cartoons. What we've tried to do is quantify how much material we've got, how much aggregate we've got, and how much monomer we've got. So if we look at these annealed spectra on the right hand side, what you can see is that when we have 100% squaraine sample, we've actually got, we claim, and we think we have pretty much 100% aggregate in the spectrum. In the spectrum we see this characteristic double humps. There's a peak here and a peak here in the spectrum. So we claim that this is our annealed spectrum. This is the spectrum of the aggregate. At the same time, whether we look at annealed or unannealed, we see when we have a 1% squaraine sample. That means the squaraine is surrounded by PCBM. It's effectively a solid solution. And what we see here is this peak at about 675 nanometers. That's a single peak. And the idea here is we can mix these together. We can fit all the spectra in between. You'll see these dotted line fits in here. The green one that you can see right here is basically a fit of the purple line in here, this annealed spectrum, and the black line down here, summed together to get a fairly decent description, which is really a little bit of the monomer and a little bit of the aggregate, and we can put those together and we can kind of quantify what how much aggregate we've got and how much monomer we've got. The problem is when we work with the unannealed samples, when we try to fit in the same way, what we find is that we can't actually do it, right? Here's 100% aggregate, and here this double hump, and what do the data actually show us? Well, we've got these strange features here. So in fact, what's happening there is we've got in the amorphous blend, we have very closely packed Squaraine materials, but rather than have molecules that are aligned in a very definite crystal geometry, what we have is a lot of molecules that are all randomly oriented, and we have different dipole interactions between these two unoriented molecules, and that's what gives rise to this. This is a dipole-dipole interaction that we start to see manifested at around 600 nanometers. So the point here is we can control, with annealing, we can control the packing of the materials, and we in principle can measure the presence of the aggregates in the monomers. We get a pretty poor fit of the unannealed materials, but we can start to quantify these things. We also label these things in different ways. This double hump in here, I'm not going to go into this right now, but we know that this is associated with an intermolecular charge transfer aggregate. We can find a whole bunch of papers from my group where we look at this intermolecular charge transfer aggregate, and we confirm that that double hump feature is that aggregate. We can also see a dipole-dipole H aggregate, and this H aggregate is what we're seeing in this region at around 600 nanometers. Okay, so where we're looking is right in here. That's a symbol of that H aggregate, and of course the monomer is down here at around 675 nanometers. What we can do is try to quantify all these things. We are definitely getting some bad fits with the unannealed spectra, but what we're looking at here is the blend ratio. So this is the amount of Squaraine. So 15 milligrams per milliliter is the maximum, or 0 is the minimum. And what we find is that at the maximum amount, the amount of monomer starts to drop down. It's a fairly linear drop. And what we also find is certainly the amount of aggregate, the amount of certainly dipole-dipole interacting species goes up. But this represents the aggregate in here at the moment. The fits aren't so good. However, when it comes to the annealed samples, what we find is that actually the amount of monomer drops pretty much to 0 at about 50% of Squaraine in the film, and what we also find is that the amount of aggregate in the annealed form jumps sort of more or less up to 100%, almost all aggregate at about 50% of the sample. So this pattern nevertheless emerges that beyond about 50% Squaraine, we pretty much get 0 monomer and more or less 100% aggregate. There's some mixture with the unannealed samples. It turns out if we look at a whole bunch of different analytic Squaraines, analytic Squaraine is this benzene ring in here with the nitrogen group on the side. And from that nitrogen group, we have these R groups. So if we increase the R group from 3 carbons in here, so this is a propyl, this is the butyl, this is a pentyl, and this is the hexyl. So as we do this, what we basically find is that there's really what this table in here signifies is that there's no real change in the crystal structure. And we've also recognized this double hump originates from aggregation, but that aggregation is coupled to an intermolecular charge transfer state. Why? Basically, the molecules are about 3.3 angstroms apart from each other, so they sort of stack on top of each other like this, and that's close enough for a charge transfer process. And again, that's described in some of the papers that have come out from my group in recent years. Very much in collaboration and very much driven by the expertise of Frank Spano at Temple University. But so we know that when these materials pack in the same way, we always see this double hump spectrum. So these are 3 of those materials from the table. And we recognize that the spectra are pretty much the same. So beyond the absorbance, what else can we think about in terms of how these devices operate? So we've actually done some space charge limited mobility measurement. And what we found also is that as the number of carbons in the side chain increases from 4 to 5 to 6, in neat Squaraine, the mobility kind of doesn't really change much. In fact, so it does decrease for the hexyl. It turns out that when we have these mixtures of the Squaraine with the PCBM, actually the mobility, the whole mobility starts to go up a little bit. But we'd pretty much say that there's really very little difference when it comes to mobilities between Squaraines with different side groups, whether it be 4 carbons, 5 carbons, or 6 carbons in that R group on the side there. So therefore we should expect similar efficiency. So what do we see? Well, it turns out that the efficiency actually goes down quite substantially from 4.5% in here all the way down to 2.24%. And these are films that are unannealed, and what we have claimed is that the reason for this drop in efficiency is because when we take the as-cast hexyl side group, Squaraine, these materials don't mix well at all with the PCBM. So all as-cast films with the DH, with the hexyl side group, they give us already these large domains, this phase separation in here. We can start to see with the pentyl groups some very small domains form in here a little bit. This is transmission electron microscopy, but really with the mixture sort of 50-50 by weight of dibutyl Squaraines in here, the TEM basically shows that these are very well mixed, very small domains. And so actually we're seeing that those small domains give us a high efficiency device. We also can see in this image that we don't really see the red curve here is the dibutyl Squaraine, but we don't see any of the double hump. So in this particular case, we're saying there's no intermolecular charge transfer state, it seems, from the spectroscopy. We also can confirm this if we look at the this is X-ray diffraction data, powder X-ray diffraction data. What we can show is that in the as-cast film, so all the black curves here are as-cast, so we can demonstrate there's no crystallinity here. There's an absence of a peak in this region, so the as-cast DBSQOH2 film has no crystallinity. When we start to anneal it, then we can bring in this crystallinity as evidenced by this peak in here. On the other hand, with the DH-SQOH2, with the hexyl side group, upon spin casting these devices, we immediately see a crystal structure. And so that's why we see the double hump in this blue curve in here on the left-hand side. So we can investigate, of course, the DBSQOH2. That's where we spend most of our efforts these days in the Collison lab. What we found again was that we get highest efficiency actually with PC71BM, But we always find that, as we've seen before, the as-cast film seems to give us the high efficiency. In recent data, we've managed to do better with the annealed films in here, but it's quite subtle. But the point here is, we've even done some solvent vapor annealing and different thermal annealing to try to increase the packing structure so that you increase the crystallinity, but maintain small domain sizes. Well, there's a lot going on here in these devices, and basically the as-cast films seem to give us the highest efficiency if we can control the crystallinity while keeping the domain size small. We seem to be doing okay, but we still have too many questions in our group at the moment, too many questions that are unanswered because of the complexity of these systems. We have questions about the importance of this aggregation. So we know that this aggregation is good for charge transfer. The charges can jump straight through, but is this aggregation the best for energy transfer? So let's take a quick summary view at the moment. We think that perhaps this aggregation negatively affects the efficiency. We've seen that in our devices. Nevertheless, we can control aggregation with annealing. The spectra tell us the extent to which the aggregation takes place with that double hump spectrum in here. We see rather the other way around. It's more like this. Phase separation we've recognized, didn't go into too much detail in here, but this occurs independently of crystallization with these materials. That double hump in here is associated with this ICT state. That ICT state, that intermolecular charge transfer state, is built upon coulombically bound H aggregates. This is where the molecules are perhaps a long way apart from each other or slightly at an angle. And we thought that maybe the disruption of this aggregation may lead to higher power conversion efficiency in here. So again, we aimed down here with our samples, but we actually wonder now if, because maybe this crystallinity is bad for energy transfer because of the fluorescence issue, because of aggregation and problems with that, maybe we actually want to have smaller domain size and we want to have a more amorphous sample. Again, very complicated system despite being such a simple molecule. So the next part here I'm going to talk about is the spectroscopy and exciton diffusion. And so what we've done is we've worked with Professor Dave McCamant at the University of Rochester, and this is a transient absorption system over there, sub-picosecond transient absorption system. We use a Thai sapphire laser, and we look at the excited state dynamics, energy transfer, and exciton diffusion. What we do is we change the intermolecular separation, and we're actually going to dope some of these squaraines into polymethyl methacrylate as a solid solution. And we can also do some work where we anneal the samples even in polymethyl methacrylate, and at some point improve the Squaraine registry. So what do we look for in transient absorption or sub-picosecond pump probe spectroscopy? How it works, so what we have here is a ground state. We've got all our molecules sitting in the ground state, and we have a sample that's got an absorption of about 0.18, and that means that the probability of getting excited is about a third. So maybe we'll imagine we come in with 640 nanometers light, and we can take 5 of those 15 molecules, and we take those 5 molecules and we pop them up into an excited state with this pump of 640 nanometers. Now the next thing that can happen is we've got this pump in here. This is the blue line that you're going to see in here, and what happens is we come through with a probe. We come in through with another pulse that arrives slightly later than the first pulse. So what happens now is, if that probe pulse comes in at exactly the same wavelength, it turns out that some of these molecules can get pushed upwards, and some of these molecules actually through stimulated emission can actually drop back down. So the other thing we might see is because the ground state in here is depleted, so there are fewer molecules in this ground state, what we find is that the absorption actually goes down because there are fewer molecules in that ground state to absorb. So as I've mentioned here, absorption is proportional to the ground state concentration. It turns out that the change in absorbance, so the absorbance goes down when the pump is on, because the pump has pushed all these molecules up to the excited state. So we come in with our probe beam. When our probe beam hits the ground state, there are fewer molecules in there, and it looks like the absorbance has actually gone down. So we register this as a change in absorption that is negative. On the other hand, if we come in with a probe pulse of 440 nanometers, what we now can address is a transition from, let's say, this second state here up to this fourth state. And maybe this transition here is an energy that's associated with a wavelength of 440 nanometers. So the absorbance at 440 nanometers will actually go up because now we have molecules in this state down here that can actually be pumped up higher into the fourth state. Bottom line here is that pump probe transient absorption spectroscopy basically gives us a change in absorbance. If the pump probe is off, then we don't see any excited states, and therefore the absorbance is zero in here with the pump on. But of course, the absorbance is positive with the pump on. So we end up having absorbance with the pump on minus the absorbance with the pump off, and that gives us our change in absorbance. For this particular case at 440 nanometers, we have a delta absorbance that's positive. This tells us basically how quickly the ground state recovers, how quickly an excited state will drop back down into the ground state. It tells us also how quickly one species will turn into another species, because different species have different absorbance spectra for the excited states that they are. They have different transient absorption spectra. It tells us which species turn into other species. So let's look at the samples. So here's what we have. We have a certain sample of squarane within a certain amount of polymethyl methacrylate. We dope from 0.01%, very low concentration, up to a pretty high concentration of 15%. This data is very similar to data that was published in 2015. This data I'm showing you today is also published in 2019. Here's how the spectra change. So basically, as we increase the concentration of the squarane, we see this peak increase, and this is these sort of dipole interactions. Well, with dilute samples, we've also looked at squarane simply in chloroform, and what we observe here is the dotted line here is an absorption spectrum, steady state. The absorption spectrum you typically measure in a standard freshman laboratory. And then what we have here is that negative value. Basically, it's the bleaching recovery, a little bit of stimulated emission in there as well. But basically, we're seeing a negative change in absorbance. That's what we expect primarily for squarane in chloroform. We also see single, so we see this ground state bleach at 650 nanometers right in here, and it mirrors the absorbance. The absorbance is right pretty much above it. We see an excited state absorbance in here at about 440 nanometers and at 503 nanometers, and that's associated with these monomers with single molecules that are surrounded by solvent. The time constants, very fast decay, 200 femtoseconds decay. We have small decay constants. They're also associated with solvent reorganization and internal reorganization of those molecules very quickly within the solvent lattice. They're not restrained in any particular position, so they can relax fairly quickly. We also see a very dominant 2.7 nanoseconds, 2700 picosecond decay that dominates for these materials, very similar to the fluorescence lifetime of, again, 2.7 nanoseconds for these materials. We compare those solvent solution data with the Squaraine in polymethyl methacrylate, very low concentrations. We again see this 650 nanometer ground state bleach. We see excited state absorbance here at 440 and 503 nanometers. And again, we see slightly different short time constants. Again, we've got a rigid solid polymethyl methacrylate, which hinders the structural rearrangement, but once again we see this dominant 2.7 nanoseconds to 2700 picosecond decay that aligns with the fluorescence lifetime of these materials. So that lifetime tau is the same in the solvent as it is in the low concentration solid solution. So it basically tells us that the polymer is a non-interacting medium. There's no intermolecular interaction between the Squaraines. So what happens as we start to increase the concentration of these Squaraines in that polymethyl methacrylate film? Well, here's what happens. So the ground state bleach for the monomer still shows up here at around 650 nanometers. We also still see a monomer excited state absorption at 440 nanometers and at around 500 nanometers. So for 15% at 10 picoseconds, already the monomer is completely gone. So we're down in here at 10 picosecond. We're looking at the green spectrum in here, right? So we're looking right in here, okay? And we're seeing that this monomer ground state bleach has gone. We're also recognizing that there's no more excited state absorption at 500 nanometers. All gone. What we find instead is we see a growth at 600 nanometers right in here, and that's a ground state bleach growth. It's the 0-1 band that increases. We claim that that is coulombically coupled, that's associated with a coulombically coupled H aggregate. So that's an H aggregate where these molecules stack together. The separation might be quite large, low concentrations, but as we start to reach around 15% doping, then these molecules start to see each other, they start to be a little closer together. So the magnitude of this growth, the growth rate and the amount of this contribution increases as the concentration of the Squaraine increases. There's no evidence of something called J coupling, right? There's no evidence of coupling between molecules in sort of a head to tail fashion. We can also look at all the spectra, so we can look at the spectra, okay, and this is at 100 picoseconds. So at 100 picoseconds, we take a spectra of all the different samples in here, and we find, again, for very low concentration samples, we have the monomer in here. It's around 650 nanometers. 100 picoseconds for the high concentration samples, that's 15%. In here, we see a peak at about 590 nanometers. We can also look at the normalized, and normalized means they're all normalized to 1 up here at 500 nanometers, and that monomer signal loss coincides with a growth in the aggregate ground state bleach at 600 nanometers. So basically the rate at which this drops, the rate at which this feature drops corresponds exactly with the rate at which the aggregate increases in its intensity, right? So they mirror one another. So here's the normalized growth of the aggregate bleach, and it basically is hard to understand in here, but if we see that the peak here for a red 15% sample, right? So 15% is red in here. We hit that maximum amount of aggregate. We hit that at about 1 picosecond. So it doesn't take much time to reach that, whereas with lower concentrations at 1%, it takes about 100 picoseconds to start to see some of that ground state bleach for the aggregate state. So next we can think about energy transfer and how that shows up in a transient absorption power dependence experiment. The power dependence comes from exciton annihilation. And what we find is that with the low concentrations of Squaraines, we find that there is indeed a small power dependence, and what this basically demonstrates is that with 80 nanojoules of pulses, so 4 times higher energy fluence, I guess, power increase, what we find is that there are now more excitons generated, and with more excitons being generated, this is a second order rate process. Those excitons need to find each other, and once they find each other, they annihilate each other, and the excited state drops back down to the ground state. So this is good evidence that when we have a low concentration of Squaraines in polymethyl methacrylate, and when we're exciting with our monomers, when we look at the excited state absorption at 500 nanometers, this is telling us that those excitons in the monomers are finding each other at low concentrations. What we also find, by the way, is that if you notice the height here for our 15% samples, the decay rate is actually rather large. The decay time is low. That's because these excitons are actually transferring into the aggregates. But we also notice that the pump power dependence is very little. There's a flat line here, a horizontal line, and that demonstrates that there is relatively little exciton annihilation that we can observe in here. And that's of course because all those excited states have migrated over to the aggregates. So these bullets basically just demonstrate what I've just said. So they're dominated by fast energy transfer from the monomer to the aggregate, and the lifetime decreases with pump power as we go to lower concentrations of Squaraine. What happens with the ground state bleach at 600 nanometers? In this particular case, we see quite substantial pump power dependence. We see these lines in here, and this basically tells us that actually these excited states in these aggregates are actually mobile. They move around. We definitely get exciton annihilation once these aggregate states are formed. So the crazy thing here, this is not expected, but the important thing to recognize is that excitons in these aggregates are indeed mobile. And it suggests, again, that first resonance energy transfer in these H aggregates actually takes place, despite the fact that these aggregates we expect to have very, very low fluorescence. And so that's really astonishing that there's so much energy transfer. It also tells us, therefore, that that's why we still actually get operating devices with these aggregates. So here's a summary of what's actually going on. Here's our monomer excited state. And what happens at very low concentrations is we do get some energy transfer as represented by this dotted line arrow in here. Of course, as we start to increase the concentration, the rate of that, and we've lost our dotted line now here, the rate of that monomer charge transfer, we call this monomer to monomer energy transfer rather, not charge transfer, increases. But we also start to get a formation of an excited aggregate state as the concentration increases and those molecules start to talk to each other. We also recognize that there is this energy transfer within the aggregates. Now, 15%, when we get to the highest concentration of squaraines, we get a lot more energy transfer within the monomer, but we also get a large amount of that excited state energy that jumps directly into the aggregate. And of course, we also get this energy transfer as we've demonstrated within the aggregate state. It's very unusual, but it certainly tells us that that's why the devices work in the first place. So moving quickly along, let's just talk very briefly in part 3, exciton diffusion in this aggregate. Why would this even happen? And then we'll conclude. So there's no J aggregate. That's interesting to many photophysicists. So also, if we did have a J aggregates fluoresce, that would allow us to understand why there would be energy transfer. But we've got, in principle, only H aggregate. Why are we getting energy transfer? So we're going to try and understand these squaraines. Where do we start? So we have used something called the essential states model to understand the double hump in films, and that was pioneered by Nick Hestand and Frank Spano with Chenyu Zhang and myself in this article from 2015. It's unconventional to use this essential states model, but it works really well for these polar materials, for these quadrupolar materials actually. We also have thought about going back to basics with a typical exciton model, a Kasha model for exciton coupling in these polymethyl methacrylate type samples. Again, we think that this peak in here is going to be associated with the H aggregate. So very quickly, what's H and J aggregation? When two molecules interact with each other, here's the plus side of the dipole and here's the negative side of the dipole. This would be a high energy situation in here with these molecules because the pluses would be right next to each other. There's some repulsion there. Of course, they're held in a crystal geometry, so they can't go anywhere. And when we excite a transition dipole moment, effectively the system picks one orientation or the other. It's a random event, but effectively this H aggregate in here, when we have a transition dipole moment with plus to plus and minus to minus, when they're stacked on top of us, that we have in fact a net dipole moment. Both of these arrows are pointing from left to right, so there's a significant transition dipole moment in here. So this would be what we would say is an allowed absorbance, right? We need a transition dipole moment in order to observe this absorbance. So it does occur. That's an H aggregate for you. The lower energy state, when we have opposing transition dipole moments, well, the net transition dipole moment, because they're opposing, is 0, but it's a lower energy state because we've got the plus charge here and the negative charge here, and they actually attract each other. So it's a lower energy state, but there's no absorbance allowed because there's no transition dipole moment. So that's an H aggregate for you. And if we have a J aggregates basically have this head to tail geometry in the ground state or in the lower state, and in this particular case we sum these dipole moments up, these transition dipole moments up. It's a low energy state because we have the minus here that's right next to the plus, so that is an attractive situation. So we do have absorbance to the lower energy state for an H aggregate, for a J aggregate, but when we have the high energy states. We've got a negative here and a negative here. They repel each other. Of course, we've also got a net zero transition dipole moment. So this absorbance is not allowed. So this is the typical understanding of the Kasha description of dipole-dipole interaction. We think that we always have vibrational relaxation or internal conversion from an excited state that's high. It drops back down the energy. The states drop back down to the lowest energy state. In principle here there'd be no fluorescence. So that fluorescence wouldn't be allowed because we got a zero net transition dipole moment. We would see fluorescence from the ground state of the J aggregate. So it turns out because this fluorescence should be zero for these H aggregates, so we should not see any fluorescence at all for these H aggregates, we think that energy transfer shouldn't be possible. And that's why we're scratching our heads here, because we've observed that there is energy transfer for these materials. Couple more slides. This is the 100 picoseconds spectra for the Squaraine ground state bleach. So these are the real experimental data. We've actually done some modeling, and I'll leave for you to read the description of these simulations. So this is a dimer absorbance spectra, and we've actually changed the separation distance from 1.5 nanometers, that's 15 angstroms, to 0.4 angstroms, and what we see is there is this sort of blue shift that makes sense, that actually looks somewhat similar to the blue shift that's seen in the experimental data. So this data basically confirms that we've really got an aggregate in here, and the energy is flowing into the aggregate initially when we excite our samples. So energy transfer to the H aggregate. So some work that we also recently published from 2019 basically tells us about the non-Kasha behavior in these very unusual quadrupolar di aggregates. Very interesting molecules these Squaraines are. So of course we can get excitation, we can get fluorescence in these Squaraines in the monomers, we can get energy transfer. I showed this earlier. As the fluorescence comes down, then an absorbance can go up. What happens is when these monomers start to interact or start to find eventually another aggregate right next to it, there's an energy transfer that we expect into that dark state of the H aggregate in here. But this transition, because there's no fluorescence allowed, is very unusual. But there's also some unusual behavior associated with these Squaraines that are described fairly well in this paper, again from 2019. So this spectrum here just again summarizes, or this slide summarizes the energy transfer that we think we see. Some of these answers are actually provided in the recent work, this published work with Dave McCammett. So in summary, going to conclude here on a cliffhanger, really. The Squaraines, we think, are representative push-pull molecules, small enough to be modeled, but also they give fairly good efficiency in devices. They're also fairly easy to synthesize. We know that the OPV performance is affected by the crystallinity, by the domain size, and by the aggregation. It's just how they all connected together. Transient absorption is great because it allows us to look at energy transfer independent of devices. These polymethyl methacrylate solid solutions are fantastic to work with. They can give us this initial study of these coulombically coupled aggregates, these dipole-dipole interactions on molecules that are fairly well separated. We are also looking at intermolecular charge transfer aggregates in films using transient absorption. Turns out that energy transfer is fast for monomers at 6 nanometers separation. And we can calculate that from the concentration of the squarane in the polymethyl methacrylate. So energy transfer is fast for monomers to aggregates, certainly as the average intermolecular separation decreases. The aggregates, excited states, are still mobile, and that's why we don't get a zero power conversion efficiency for our devices. They still work. Definitely have to look into this more because of this H aggregate Forster resonance energy transfer. There must be a zero orbital, zero overlap integral here, so we wouldn't expect to see that energy transfer, but it nevertheless happens. The idea here, though, life goes on, research goes on. Our goal is always to better understand these materials, and once we understand the materials, new materials, better understanding, and in principle, one day we will save the world from this climate change catastrophe. So thank you for listening. Again, we hope that we can understand exactly where this red dot needs to be. I'm going to finish with some acknowledgements, and this work was supported by the National Science Foundation. A big thanks in theory, Frank Spano, Chenyu Zhang, Nick Hestand, and also Dr. Chue Zhang, Tyler Wiegand in my group currently, and some transient absorption work here with Dr. Michael Mark and Dr. Dave McCammont at University of Rochester. Dr. Jeremy Cody made the materials, and a lot of students were involved in characterizing some of these devices, and in particular thankful for Dr. Zhang for all his efforts, as my PhD student graduated a couple of years ago in 2017-2018. And thanks for your attention.